When we use optical fiber in a system, whether it is telecommunication system or a sensor system, we come across the instances where we need to join two fibers together. And when we make a joint between the two fibers, then there are always some losses. These losses are known as the splice losses. In this lecture, we will study about the splice losses. So, the fibers which we join can be identical or non-identical. For example, if I am joining two telecom fibers together, then these fibers are identical, but when I am putting some telecom component which is also made of fiber itself, then this fiber can be different from the telecom fiber, its specs would be different from the telecom fiber, and the two fibers I am joining now would be non-identical. When I put two fibers together, so howsoever precise alignment I do, there are always some degree of misalignment, and these misalignments, even if very small, they can cause significant losses. And in case of two identical fibers, even if there is perfect alignment, because of the difference in the fiber parameters, there are always some losses. Basically, the mode of one fiber would be different from the mode of the other fiber, and because of this mismatch between the modes of two fibers, there would be a loss, and that is known as mode mismatch loss. So, what are the various types of misalignments? Let us first look into that and then calculate the expressions for loss corresponding to these misalignments. So, one type of misalignment is in the transverse direction, that a fiber is shifted, one fiber is shifted with respect to another in transverse direction. Another is angular. When you join two fibers, there is some angle between them. This is highly exaggerated. This misalignment is of the order of a degree or so. This can be caused due to your finite precision of the stages at which you are putting the fiber, or due to not very sharp, and in the transverse direction, if this cleaving of the fiber is not perpendicular to the axis of the fiber. So, ideally what you should have, when you have two fibers and you want to join them, then you first cleave the fibers. So, this surface should be perfectly perpendicular to the fiber axis, but if it is something like this, then it will cause angular misalignment loss. Third is that if there is a small gap between the two fibers, then there would be a loss. So, I have transverse, angular and longitudinal misalignment losses. Let us work out the expression for loss in case of transverse misalignment, and in this entire lecture I will use Gaussian spots and Gaussian spot sizes of the modes of the fiber, and I will restrict myself to only single mode fibers. So, I have fiber 1 which has a spot size W1, this is Gaussian spot size, and I have fiber 2 which has a spot size W2. This direction is Z and this is X. So, in whatever direction there is transverse offset, I can choose my X axis along that, and accordingly I will choose my Y axis perpendicular to X and Z. So, now what I can do, I can write the Gaussian mode of this fiber, and let us say the mode of this fiber is centered at 0 0 and has size W1. So, the modal field would be given by psi 1 x y is equal to square root 2 over pi times 1 over W1 exponential minus x square plus y square over W1 square. Now, this fiber is shifted with respect to this by an amount u in x direction. So, the mode of this would be centered at u0 and it has a size W2. So, the Gaussian mode corresponding to this would be given by this should be psi 2. Psi 2 x y is equal to square root 2 over pi 1 over W2 exponential minus x minus u square plus y square over W2 square. Please make a correction, this is psi 2. And in order to get these, I have used the normalization condition that mod psi square dx dy integrated over the entire range of x y is equal to 1. Since I am using these to calculate the losses, so these are basically area normalized. Now, how do I calculate loss? Well, calculation of loss is very simple. I have a Gaussian of one fiber and Gaussian of another fiber, then the overlap between these two fields will give me the loss or the fraction of power that is coupled from one fiber to another fiber. So, the fraction of power that is coupled from one fiber to another fiber would be given by T is equal to integral minus infinity to plus infinity, integral minus infinity to plus infinity over x and y psi 1 psi 2 star dx dy mod square. Okay. So, this is the overlap integral, and if I take its mod square, then it will give me the fraction of power coupled from one fiber to another fiber, and this expression is true when these modal fields are normalized according to the condition which I have stated in the previous slide. So, now if I use the expressions for psi 1 and psi 2 which I had written earlier and do some mathematics, then I will get the expression for T as T is equal to 2 W1 W2 over W1 square plus W2 square whole square times exponential minus 2 U square over W1 square plus W2 square. From here I can calculate the loss in dB. I know this T is nothing but P out over P in. So, loss in dB would be 10 log 1 over T. I can see from here that if the two fibers are identical and there is no offset loss, then this T should be equal to 1, and I can check that out. If W1 is equal to W2, then this term becomes 1, and when U is equal to 0, this term becomes 1. So, from this expression of fractional power coupled from one fiber to another fiber, I can estimate the loss which is purely due to mode mismatch, and in order to get this loss which is known as mode mismatch loss, which is purely due to mismatch in the modes of two fibers, I should put U is equal to 0. So, in order to remove any contribution from transverse misalignment, so I put U is equal to 0. If I put U is equal to 0 here, then alpha in dB would simply be minus 20 log 2 W1 W2 over W1 square plus W2 square. I can divide this numerator and denominator by W2 square, then I will have W1 over W2 here and W1 over W2 square here. If I define this W1 over W2 by F, then it can be written as minus 20 log 2F over 1 plus F square. Now, let me plot this mode mismatch loss as a function of W1 over W2. Then I can see that if W1 is equal to W2, then there is no loss, loss is 0 dB. but if W1 over W2 is smaller than 1, that is W2 is larger, or if it is greater than 1, that is W1 is larger. In both the cases I will have mode mismatch loss. Let me zoom it to a level of 0.1 dB, and when I do this, then I find that to keep the loss below 0.1 dB, to keep this mode mismatch loss below 0.1 dB, the mismatch between the spot sizes should not be more than about 15%. So if you have a mode mismatch up to 15%, then your loss, this mode mismatch loss would be less than 0.1 dB, and this kind of analysis is very handy and very useful when you estimate the loss, or when you design your fiber components to be used in telecom system. So you always design the components in such a way that the fiber you are using for them should not have mode mismatch with the telecom fiber more than 15%. Now let us calculate the transverse offset loss for two identical fibers. So this is the fractional power, and for two identical fibers W1 is equal to W2, and let us say it is W, then this T would become simply e to the power minus u square over W square, because this will become 1. And from here I can immediately get the transverse offset loss in dB as alpha T is equal to 4.34 u square over W square. So I can see from here that if W is small, then your transverse offset loss is large. If W is large, then the tolerance towards transverse offset loss is higher, because the loss is smaller. So to see this graphically, I have plotted this transverse misalignment loss or transverse offset loss as a function of u, that is transverse misalignment, for different values of W. Okay. You see that this x axis has the same range in all the figures, while if you look at the y axis, that is the loss axis, you look at the numbers, and these numbers decrease as I go for higher values of W. So for higher values of W, the transverse offset loss is smaller. Now let me look at 0.1 dB level for a telecom fiber which has a spot size typically 5 micrometer. So for W is equal to 5 micrometer, in this figure if I look at this line which corresponds to loss is equal to 0.1 dB, then I find that to keep the loss less than 0.1 dB, U or transverse misalignment should be less than 0.76 micrometer. So this is the degree of precision with which I should align my fibers while making a splice, while making a joint. Another misalignment is in angular direction, and it causes angular offset loss. So I have fiber 1 with a spot size W1, fiber 2 with a spot size W2, and this is tilted with respect to fiber 1 by an angle theta. So again what I will do, I will use Gaussians here, Gaussian mode of this fiber and Gaussian mode of this fiber, and I will have to take the overlap of them. Now how I will take the overlap? Well, I will represent the Gaussian of this in the rotated coordinate system. So this coordinate system is now rotated by an angle theta. So I have this x prime and y and z prime, x prime and z prime, which is rotated by an angle theta. So I should do coordinate transformations. So the coordinate transformations are like this, which relate x, y, z to x prime, y prime, z prime. Now I can write down the the Gaussian mode of fiber 1 like this, and Gaussian mode of fiber 2 like this at z prime is equal to 0, and this is at some z, where this n here and n here is the refractive index of the material which goes in the gap between the two fibers. And usually this material is nothing but cladding material, because when you join two fibers you align them and then fuse them together. When you fuse them together, the cladding material gets melted and it goes in the gap. So this n is nothing but, most of the time it is cladding material. So again I can find out the fractional power coupled from fiber 1 to fiber 2, okay, by taking the overlap of these Gaussians, and then it comes out to be T theta is equal to 2 W1 W2 over W1 square plus W2 square whole square exponential minus k naught square n square theta square W1 square W2 square divided by 2 W1 square plus W2 square. In order to get this expression, I have assumed that the value of theta is small, so that sin theta is equal to theta and cos theta is equal to 1. If you want to look into more details about this, then you can refer to the textbook Introduction to Fiber Optics by Ghatak and Tyagarajan. So this is the fractional power coupled from one fiber to another fiber, and from this now I can find out the angular offset loss for two identical fibers. So where I have now W1 is equal to W2 is equal to W, and this gives me T theta is equal to exponential minus k naught n theta W by 2 whole square. So the loss, angular offset loss in dB would simply be now given by 4.34 times k naught n W theta by 2 whole square. So this is the angular offset loss. Here I can see that if W is large, then angular offset loss is large. So I have plotted it. I have plotted this for different values of W, and I can see that when I increase the value of W, the angular offset loss increases. And again I look at telecom fiber, which has approximate value of W as 5 micrometer and 0.1 dB loss level. So I can see that if I want to keep the angular misalignment loss below 0.1 dB, then theta should be less than 0.6 degrees. So with this precision I should align my fibers, or with this precision I should cleave my fiber, okay, so that it is perfectly perpendicular. It is perpendicular to the axis of the fiber. The last one is longitudinal offset loss, which occurs when you join two fibers together and there is always some gap left between them, and when you fuse them, then cladding material goes in the gap. This also causes loss because the Gaussian mode, when comes out of this fiber, it diffracts, and when it reaches to this end of the fiber, then this diffracted Gaussian would be different from the Gaussian mode of the fiber 2. So in order to estimate this loss, what I should do, I should take the overlap between the Gaussian of this fiber and diffracted Gaussian of this fiber. So when I do this, then I can find out the longitudinal misalignment loss, and it is given by alpha L in dB is equal to 10 log 1 plus d by k naught n W square whole square. So here I have plotted this for various values of W, and I can see that this longitudinal misalignment loss decreases as I increase the value of W, and it is understood that if I have a small value of W, then the diffraction would be large, and if diffraction would be large, then the diffracted Gaussian would be very much different from the Gaussian of fiber 2, and it will cause more loss. Okay. So, for larger value of W, the longitudinal offset loss is smaller. Again let me look into the values of loss which are close to 0.1 dB, and for that I have increased the range of longitudinal misalignment while plotting this loss curve for W is equal to 5 micrometer, and what I see that even for longitudinal misalignment as large as 20 micrometer, the longitudinal offset loss is smaller than 0.1 dB. Okay. So, longitudinal offset loss is not a major concern for us. Okay. It is not a major concern for us. However, the transverse and angular offset losses are quite large if the misalignment is large. Let us work out an example, a numerical example. So, I consider two identical step index optical fibers with N1 is equal to 1.45, N2 is equal to 1.444, and core radius A is equal to 4.2 micrometer, and I want to calculate at lambda naught is equal to 1.55 micrometer all the three losses for various values of misalignments. So, let us see how do they come out. So, the transverse offset loss for U is equal to 1 micrometer. Well, so at lambda naught is equal to 1.55 micrometer, if I calculate the Gaussian spot size, it comes out to be 4.81 micrometer. The easiest way to find this out is you first find out the value of V, and then using the empirical relation you can find out the value of W for Gaussian spot size. So, it comes out to be 4.81 micrometer. Now, you can calculate transverse offset loss by the formula alpha is equal to 4.34 U square over W square, and it comes out to be 0.19 dB. The next part is angular offset loss for theta is equal to 1 degree. So, again you find out the Gaussian spot size, W is equal to 4.81 micrometer comes out like this, and then you find out angular offset loss by the formula 4.34 k naught N2 W theta by 2. You see that instead of N I have put N2 here because N2 is the cladding material, and this is the cladding material which goes inside the gap. So, angular offset loss comes out to be 0.26 dB. Third is longitudinal offset loss for D is equal to longitudinal misalignment D is equal to 10 micrometer. So, again the Gaussian spot size is 4.81 micrometer, and if I calculate the longitudinal offset loss using this formula, then it comes out to be 0.023 dB. So, again look at these figures that longitudinal offset loss is 0.023 dB, the angular offset loss is 0.26 dB, while the transverse offset loss is 0.19 dB. So, I can see that I need to, when I join two fibers, I need to precisely align the two fibers in transverse and angular directions in order to have as low loss as possible. So, this is all in this section in this lecture, and what is left is another very important characteristic of a single mode optical fiber, and that is waveguide dispersion. So, in the next lecture we would look into the waveguide dispersion and subsequently the total dispersion, and this will give me what is the data carrying capacity of a single mode fiber. Thank you.